Oh, wow. Thank you for the kind introduction. And also, it's great to be here. I really thank Professor Delanlis for the invitation. First time giving a talk here. So today I want to talk about my recent work with Sung-Jin Oh and Dong-Ho Chae about degenerate dispersion and ill-posedness for the generalized SQG. This is going to be completely elementary, so please do not hesitate to interrupt me with any questions you have. So my goal is to give you some understanding of how we should deal with degenerate dispersive equations. So many of you probably haven't encountered these equations, but if you do, it will be kind of good to know. But okay, so I will start with some prototypical examples. Examples of degenerate dispersion. So this kind of equation first appeared in the physics community where people started to consider equations of the form dx of u times squared u, and many lower order terms. And of course, there are like many variations of equations of this type. The point is that if this coefficient was not there, this is just linear KdV equation. And you can put, instead of u, any other function of x in u. And this kind of equations actually appear in many areas of physics. And for instance, in the shallow water wave problems, sedimentation, flame propagation, and I will show you a concrete example in magnetohydrodynamics. And okay, so these equations appear in physics, and the interesting thing happens when the solution u vanishes at a point, because then you have that the coefficient of the leading order term vanishes, and this is called to be degenerate dispersion. The leading order term is dispersive, but it is degenerate at a point. The coefficient vanishes. Okay. And of course, the sub-principal terms, the lower order terms, they do matter, but in some sense, they're not essential part of the equation, or the essential information is contained in the principal term. And you can always modulate the lower order terms by some change of the dependent variable. Okay. Okay, so the question, the very basic question is well-posedness in the case of degenerate dispersion. Even local well-posedness. And essentially, this was completely open until like a year or 2 years ago, when there was some work by Germain, Harold Griffiths, and Marzola, where they proved a very special kind of well-posedness for one of these models. But they really need to use some special structure of the equation for their well-posedness theory. So I'd say that the general well-posedness theory is still completely open. And what I want to talk about mainly today is on the construction of so-called degenerating wave packets, which in particular show immediately that this kind of degenerate equations are ill-posed in any standard function spaces you can imagine. And also they provide necessary conditions on the function spaces which could potentially allow for well-posedness. So this explicit approximate solutions kind of dictates in which function spaces these equations have a chance of being well-posed. Okay. So that is the point I want to make. But the heuristics, which allows us to tell in which function spaces they could be well-posed or not, comes from simple bicharacteristic analysis. Which I will now explain. Any questions? So let's say we have a simple linear equation. So everything is just scalar valued and x is one-dimensional. We're in the simplest possible case. And this is the equation. Let's say we have I times some real valued functions dx times some Fourier multiplier p of d applied to phi is 0. You can have lower order terms, but let's say this is the equation. This equation arises, for instance, when you linearize the quasi-linear problem around some specific solution which crosses 0. Okay. This is just a linear problem. B and P are some real valued functions and multipliers, which is degenerate in the sense that let's say d of 0 is 0, and b is a smooth function. This is what degenerate means for me, and it is dispersive. Dispersive simply means that for me, this TC of P goes in P when the frequency goes in P. Okay. So this is what I will call degenerate dispersive equation. Okay. So how should we understand the solutions to this equation? And this is precisely given by the bi-characteristic ODE system. So the idea is completely elementary, and it goes back to probably Hamilton, more than like 150 years ago. So the ansatz you make is that the solution is given by the exponential of I, C, G, time-dependent frequency times some amplitude function, which is very smooth, and it is localized near some point. So this is what we call roughly a wave packet. It means that the function is localized, reasonably localized, both in frequency and in space. And then you formally plug this ansatz into the equation, and then you get a system formally of ODEs for the frequency and the space location of the wave packet. And this is the famous Hamiltonian ODE system. So C dot is dx of this, dxb evaluated at x times p evaluated at c, and x dot is minus of dx c p evaluated at x. Okay. So given b and p, this is a completely explicit system of ODEs, which can be solved if you just specify the initial frequency and the initial space location. And what you will see is that the Hamiltonian, which is the x times p c, is supposed to be conserved along the solution. However, this is degenerate. By definition, it means that it vanishes as x approaches the degeneracy. However, the product needs to be conserved. So if you can arrange the solution in a way that x approaches 0, then immediately it shows us that the frequency should grow. And the rate of growth of the frequency is exactly the same as rate of convergence to the point of degeneracy. So formally, based on this ODE, you can kind of easily see that this linear equation is supposed to be ill-posed in any high regularity space. And I can easily show you a concrete example. And we can take that example, for instance, kind of where started. So here's an so in that equation, if you take u to be x cubed, it is kind of an explicit solution. So you can try to linearize around that explicit solution, and that gives this equation: I plus I, so without I, x squared, 5 plus all the lower order terms. And as I told you earlier, the structure of lower order terms is not so important. You can always change variables to mathematical lower order terms in the way you want. And the symbol corresponding to this is simply I x squared times c squared. So the corresponding bi-characteristic ODE is simply that C dot is 3 x squared c cubed, and x dot is minus 3 squared. Sorry, x cubed c squared. And this is preserved. So xt ct equals x0 c0 4 times. So this is very easy to solve. This is in particular equal to 3 times c times this squared, which you can immediately integrate, and you can do it for x as well. So t is c0 exponential of 3 squared times t. Okay. And now what you see is that frequency grows exponentially. Okay. And this is really bad because the rate of growth depends on the initial frequency. So any reasonable function, say in HS, will have at least some part of its frequency which is located very large at the initial time. And this is telling us that formally, if you believe in these heuristics, that part of the solution will grow exponentially with the rate depending on the frequency. So this is really bad. And the picture is very simple. This is the point of degeneracy. This is x. This is, let's say this is your initial wave packet, which you can initially separate, completely separate from 0 by taking this to be 1. But you can take the initial frequency to infinity while normalizing x0 to 1. And you can also normalize the equation in a way that, for instance, the L2 norm is conserved. That is done by introducing suitable subprinciple term. But if you do it, then what you can see is that while keeping its L2 norm, the solution should grow like this. If it keeps its L2 norm, the physical support of the solution should be getting squeezed exponentially according to this rate. So if the lesson is very simple, if you normalize the equation in a way that the L2 norm is preserved, all the higher overlap norms will blow up. Okay. So this is the lesson from a simple ODE analysis. And basically what we do is to make this precise by constructing actual solutions, or to be more precise, approximate solutions, which precisely exhibits this behavior. And then from this, we can deduce all these ill-posedness results. And more importantly, they really dictate what could be the well-posedness function space look like. So in this case, this is really, really difficult. What this is saying is that the well-posedness test should be designed in a way that C part of the initial data should somehow be able to accommodate this growth. So large frequency should be extremely small in a way depending on the frequency. Okay, so the main question is the following. How do we really make this precise, construct the solution with X and C localized for a reasonably long time in which this behavior is actually observed? Okay. And we will come back to this question, but this is just the picture. Okay. Any questions? And now I want to just introduce you the generalized SQG equations. Okay. Because surprisingly for us, this family of equations provide a wonderful family of degenerate dispersive equations in a kind of unexpected way. And they also appear in some physical situations, as I will explain. So the domain is, let's say, we take it to be the two torus, and then there's time, and it's a real value function. And the evolution equation is just the transport in 2D. But at each moment of time, the velocity is determined from the scalar theta by some constitutive law. This is just some Fourier multiplier to be made precise. So this is so-called the family of generalized SQG equations. And of course, the most well-known example is 2D Euler. When you take gamma to be a Laplacian increase. And this is what is called 2D Euler. And SQG is when this is its fractional power. So at this point, I want to draw you some diagram. So based on these two examples, people have been studying a lot this generalization, so-called alpha SQG equation, where you simply take gamma to be minus alpha power of the Laplace. Or let me say alpha over 2 so that alpha becomes the unit of order. Okay. And the main question that people have been asking is whether the solution to this equation blows up in finite time or not. So for those who are not familiar with these equations, 2D Euler is globally well posed. And still, it's a wide open problem whether solutions, smooth solutions to SQG, or even the generalized SQG could blow up in finite time. So a fun story is that after Tarek El-Guindi posted this groundbreaking result on blow up of 3D Euler, people immediately jumped on adapting that proof to SQG and this equation, but they absolutely failed. These equations are different from 3D Euler, and in some sense they are more different if you want to prove blows. Anyways, that's not really related to this talk. And here's some diagram. So this is a family of generalized SQG equations. And alpha is really this alpha, which is the power of the Laplace. So the equations becomes more regular in this way. And when alpha is 2, this is 2D Euler. When it's 1, this is SQG. And you see that at this point, theta is of the same regularity with the velocity. And when it is 0, it's kind of interesting because it means that gamma is the identity operator. And in that case, this nonlinear term is grad perp theta dot grad theta, which is identically 0. So the equation is completely trivial in this case. There's no equation. And now I will show you that the values -1 and -2 corresponds to some physical equations. This corresponds to so-called pole MHD. I will explain in a second. And this corresponds to so-called the asymptotic model in the large-scale geostrophic equation. Okay, so before I move on, I want to discuss the conservation laws of these equations. First of all, velocity is always incompressible, no matter what this multiplier is. So all the LP norms are conserved. Of course, I'm interested only in the coercive conservation laws. First of all the LPs are conserved. And there is another interesting conservation law, which is gamma 1/2 of theta in L2. This you can see by computing DDP of gamma theta dot with theta dx, which is of course the same as gamma 1/2 theta raised to power 2. This is C. If you just look at this equation, there's grad pulp of gamma theta, which cancels gamma theta. And this is nothing but the kinetic energy when it is Euler. What is interesting is that when gamma is singular in the sense that gamma of C becomes infinite as C goes to infinite. So this I will refer to as a singular region of generalized SQG. So in this picture, this is the singular region. What's interesting is that at least on the L2 basis, this becomes a stronger conservation law than this as soon as the multiplier becomes singular. And recall that there is also this special cancellation when gamma is the identity operator. So it has been kind of well known that when gamma is not singular, in the sense that this remains decaying or bounded as frequency goes to infinite, there is local well-posedness at least. Okay. So local well-posedness when gamma is not singular. And when gamma becomes singular, you have now this conservation law, which is stronger than LP of theta. So you might expect that there is some hope for well-posedness, but our main result shows that as soon as gamma becomes singular, it is completely ill-posed in any reasonable function spaces. And the idea is simply the observation that as soon as gamma becomes singular, the generalized SQG is a degenerate dispersive. But before going into the statements and proofs, let me explain some situations where singular multipliers actually appear. And I want to be quick about this. So, okay, examples of singular multiplier. First, I want to mention some models, so-called Okitani model. Which is basically when gamma is log of C. And this was introduced in a paper of Okitani. He was a physicist. And the reason that he obtained this model is that he was interested in the collective behavior of solutions for varying alpha in the regular regime. So he was considering for the same initial data, what happens if you change this value alpha in the region which is not singular. So namely when alpha is strictly positive. And then he realized that the solutions are kind of convergent when alpha goes to 0. And this is not surprising because, so this is what he does. If you look at the nonlinearity, which is alpha over 2 theta, the gradient theta. First, this is equal to this minus 1 theta. Minus 1 theta, the gradient theta, because this cancels with gradient theta. And if you divide this by alpha, which is just dividing, multiplying the time variable, you are stretching the time variable. This formally converges as alpha goes to 0 to the log. And this is what he actually observed by numerical simulations. So his goal was actually try to observe some singularity formation in the alpha SQG equations. Instead, he was observing global regularity, and then he kind of explained it in terms of this convergence. Of course, he didn't care about whether this equation, the Okitani model, is well-posed or not. But if this is well-posed, then this gives some indication that the alpha SQG equations are also globally well-posed because you have this time stretching factor alpha. So basically, this is telling you that if Okitani model is well-posed for time 1, the alpha SQG is well-posed for time 1 over alpha, which is huge when alpha is small. And then there is this whole MHD equation. I'm not going to write down the full system, but the important part of this equation is this funny bilinear form. So B is a vector in 3 space. So this is the whole MHD equations. And there are many associated history. And this bilinear product, in the simplest possible reduction that you can do, corresponds to generalized SQG with -1 arc, which is in the singular region. So the ansatz, which we figured out, is that you can take B to be approximately something like this. This is kind of funny. Some scalar function psi, and you take this ansatz. Ez is the unit vector in the z direction. So its z component is this scalar function, and the xy component is this. Then you can formally see that this scalar function psi satisfies the GSQG equation. With 1/2. And lastly, I will not explain how this equation can be obtained. The so-called asymptotic model reads psi is now some stream function, and the equation is exactly this. And you can find it in the literature, for instance, in several papers of literature. So this is the opposite of 2D Euler. Instead of Laplacian inverse, you now have the Laplacian, which is kind of crazy. So our main theorem says that all of these equations are completely ill-posed in reasonable function spaces. In reality, what it means is that these equations should be considered with appropriate dissipation operator as well. And our ill-posedness results should be able to give enhanced dissipation for the physically correct dissipation equations. So let me briefly write down our main theorem, which I already told you. Main theorem is that GSQG equations are ill-posed in the sense that strong norm inflation occurs, or the hypothetical solution are ill-posed in HS with S sufficiently large, depending on the multiplier gamma. To be more precise, we can even show that when gamma has some order which is strictly negative or strictly positive, then gamma is stronger than 1/2 for some positive alpha. It means that gamma is positive order. Then we can even show that it is ill-posed from HS to HS prime, with S prime strictly less than S. for all S and S prime sufficiently large. And the gap depends on the size of R. So even if you are allowed to lose regularity for the solution, there is still ill-posedness. And the case of log is more delicate. Or you can even consider cases which are even weaker than log, for instance, log or log. In this case, you can actually prove that there is well-posedness theory in the scale of time decreasing Sobolev exponents. So if S is sufficiently large initially, so this is initial data, and if you demand your solution to be in a Sobolev space with exponent decreasing with time, then there is uniqueness and existence in this function class. In other words, you are not allowed to have this kind of gap loss ill-posedness. But we can still prove ill-posedness in the same HS spaces for all S large. So this gives some kind of well-posedness theory to the Okitani model, which allows one to get long time existence for alpha SQG.
How do you define exactly the ill-posedness? So it's not in the solution is not in the space, or is it inflation of the norm?
Yes. Right. So that's important because there is a delicate point because there is no existence basically, but so the precise statement in the case is that there is a sequence of initial data, theta 0 epsilon, which are completely smooth and converging in HS as epsilon goes to 0. There is a sequence of initial data such that either there is no solution at infinite in time with values in HS prime for any time interval, or there is one but has strong norm inflation, so that the norm becomes at least of size 1 over epsilon in a time interval which becomes shorter as epsilon goes infinity. Yes. But using this as a building block, when the domain is either t times r or r2, we can actually prove non-existence because you can just attach these building blocks in the non-compact direction. And this is coming from the linear ill-posedness results, which I will now explain. So this is just an annoying fact that it should be stated in this way because we do not know the solution exists in, even if we consider like really good aesthetic. Any other questions? Okay, so the main nonlinear theorem is coming from a main linear theorem. And for the sake of presentation, we can consider shear flows, which are kind of explicit. So for instance, if you take solution, which is, for instance, x2 squared over 2 near x to 0. So any function which is a function of the second variable only is a steady state. This is a shear flow in terms of the velocity. And you can write down the linearized equation around this steady solution. And the equation is simply let's say this is f of x2, if you don't mind. But we want this to be degenerate. We want this to be a degenerate steady state. This is the so it's kind of simple. There are two terms. They differ by whether the multiplier has fallen on our function or on the profile f. These are just two terms. And of course, this is the principal term for us. But if gamma is kind of not so singular, like log, these two terms kind of become indistinguishable. So actually, for the proof, it's kind of technical, but easier case is when gamma is more singular, which really separates these two terms. In any case, you can immediately do the bicharacteristic analysis for this principal order term. And then you can see immediately that at least on a heuristic level, wave package must be ill-posed. Because this multiplier, I mean, even neglecting this dx1, which you can separate away. So we can separate this away by rewriting phi with I lambda 0 x1 times phi of T and S2 with some abuse of notation. This dx1s becomes simply multiplication by I lambda. So if you allow me, the equation is simply ddt over I lambda naught, or I will write I here, I times this, I times this. So you see that this is degenerate dispersive. This is dispersive in my definition because this is singular, and this is degenerate. So you see why we need at least a quadratic profile f, because there is at least one derivative falling on the profile always. So here is the main linear theorem, which basically says that we can construct solutions which behave exactly like the bicharacteristic analysis. Linear theorem. So this is kind of formulating the optimal way possible. So you take some frequency amplification parameter m, which can be very large. Then tau m is the time it takes for frequency lambda naught to grow to be m times lambda naught. And this is really coming from the bicharacteristic ODE. We define tau m to be the time it takes for the frequency, initial frequency lambda naught to become m lambda. This is given by. So this is the multiplier. Divided by lambda. And you can say that this is a small time. And the main growth theorem is that primo. I'm not really telling you all the necessary assumptions on the multiplier, but we can consider multipliers under very natural assumptions. For instance, the derivative of gamma should decay and is one order faster than gamma itself, and so on. This primo in time over this time interval of linear solution phi measured in HS prime should be greater than initial data in HS times square root of gamma lambda naught divided by square root of gamma lambda naught times m lambda naught multiplied by m times s prime lambda naught s prime minus s. And you should remember that even for the linearized evolution, gamma 1/2 of theta, of phi is preserved, same as the nonlinear evolution. So, and that was the change of dependent variable that I was talking about. For any degenerate dispersive equation, essentially any, you can always modulate the dependent variable in a way that the L2 norm is conserved. And then you are asking what is happening to higher norms. So for the case of this particular equation, what is happening is that gamma 1/2 of theta is stable in L2 for this particular subprincipal order term. So you should consider this in a way that this square root comes with the solution because we want to measure the solution in m lambda naught, and the initial data comes with this square root. And what this is giving us is this growth of m to power s prime. This power of lambda naught is coming from the initial data. Okay, so I should tell you that the initial data is assumed to be concentrated around frequency lambda naught. And then we can prove that this growth must hold. So for any lambda naught and any large m, we can construct initial data which is supported near frequency lambda naught such that any, because we don't have uniqueness to the linear problem, any solution to the linear equation must satisfy this growth.
Maybe I missed it, but what's the little gamma again? So you have like a square root of little gamma?
Oh, this is just a multiplier, sorry, it's just a multiplier. And this is really paired with this. This is really paired with this because this is the conserved quantity. And what you get is this. And also, as lambda naught goes to infinity, and if you fix m and send lambda naught to infinity, tau m goes to 0. So arbitrarily small time, you get arbitrarily large growth. This is what this gives. So So I will just end with the outline of the proof in the simplest possible case. And maybe this is too simple, but it's a nice computation. The last part is this is linear result. Last part is proof in the simplest case. And for the show case, I can take the case when gamma is really the Laplacian. This case, the equation does not involve any non-local operators, so that is really nice. And the equation is simply this. And I want to make this reduction to remove x1 dependence in a trivial way. X1 frequency is fixed to be lambda naught. And then you get this equation. And I also want to take f of x2 explicitly to x cubed over c to simplify computation. We can take any power which is larger than 2 as well. Then the equation becomes lambda naught inverse dt5 is I times x2 squared. This comes from taking the derivative and minus lambda naught squared plus dx2 x2 applied to phi plus rho. So this is the Laplace. So how do you really understand the solutions to this? I'm just going to directly give you the answer, but there is some trial and error that you need to go through. The correct time variable turns out to be lambda naught squared times t. So the actual motion is occurring very fast. It turns out to be the correct time variable. And in this local case, there's a very nice change of independent variables that you can do, and which is the reason I took this profile. You can take eta to be new independent variable, which is log of x2. The purpose is that you see x2 squared and two derivatives in x2. So this makes x2 dx2 to be the eta. So in this change of independent variables, the new equation becomes kind of constant coefficient. Not exactly, but essentially. And then the new equation is the tau phi is lambda inverse I times the eta phi, and there's one term, one lower order term, and this term coming from this, because x2 is exponential of eta plus even lower order terms which I neglect from the beginning.
You're assuming your solution is supported on x2 bigger than 0?
Exactly, yes, exactly. And yes, that's a very important point, because from the bicharacteristic analysis, this is x2. What you can easily check is that if you start from the right of x2, the solution is supposed to move leftward. So you want to start in this region and only in this region, on which we kind of flatten the coordinates in a way that the leading order term is now constant coefficient. Of course, this trick doesn't work in the general case, but This is very kind of illustrative. Then you see that the leading order term is just a linear Schrodinger equations, and wave package for linear Schrodinger is very well known, but now with a lower order term, and this makes a difference. In any case, now the standard recipe kind of works. The recipe is expansion in frequency. So you write down your ansatz of the solution. Now I'm putting tilde because this is only going to be an approximate solution, not exact solution, to be in tau eta coordinates, and inverse exponential of I lambda, not phi eta times amplitude in tau eta. And the goal is to be able to pick the phase function and the amplitude function as a completely smooth function of tau and eta. So you just brute force plug in this ansatz to the equation, and you can group the terms in order of lambda naught, powers of lambda naught. So as a general rule, the highest power comes when all the derivatives hit the phase. That's the general rule. And this equation, the highest order equation, does not involve the amplitude. And in this concrete situation, the resulting equations are d tau phi plus d eta phi squared is minus e to 2n. And the next order in frequency, if you group all those terms, give an equation for the amplitude, and as a general rule, it is always a transport equation. And in this concrete situation, the transport operator is d tau plus 2 times d eta phi, d eta applied to A is some nice function, assuming that phase is nice, times A. So these are very explicit, simple PDEs. This is Hamilton-Jacobi. This is transport equation. You first solve the phi, and then it can be fed into the transport equation. But here there is some kind of secret recipe. And the thing is that there is some especially nice choice of initial data for the phase function. In principle, you can pick any initial phase and solve the Hamilton-Jacobi equation, but what you want for practical purposes is that you want the high derivatives of the phase function to not grow too rapidly as tau goes to infinity. And that really depends on what you prepare for the initial phase function. In other words, you want the characteristics of the transport operator to be as flat, as parallel as possible, even when tau becomes large. So there is this notion of coherence in the physics literature that this wave package, this wave package that we are constructing have frequency going to infinity. And their space location is becoming more and more localized at degeneracy. So they cannot be really coherent forever. There exists a limiting time after which it no longer really makes sense. And that comes here when the higher derivatives of phi and then A becomes out of control. And then we want to delay as much as possible, and associated to that problem is the choice of particularly nice initial phase function, which becomes very important in the case when gamma is just a slightly singular multiplier. But This is really the idea. And after solving this, solving for the phase and amplitude, what you can do is you can directly plug in what you have in the equation, and then you can check that phi tilde is a solution to the linear equation with small error in L2. There will be an error because we have neglected many lower order terms. And in the final step, this is actually an important step, although it is simple. In the final step, there is a procedure called wave packet testing method, which first appeared in a work of Ephraim and Tataru. You want to test in L2 your solution. So this is an actual solution to the linear equation against the wave packet that you have just constructed. And what you do is you take the time derivative. Under the normalization that L2 is concerned. So if phi tilde is an actual solution to the linearized equation, then this is exactly 0. But since this is a solution up to an error, what you get is this is phi comma f. But this, by our rule, is small in L2. So what this gives is that this absolute value is small. Okay. And the punchline is that then this L2 product at time t is similar to the initial L2 product. This is explicit, and we can explicitly take the initial data to be this. So this is approximately the same, but we know everything about the wave packet solution. This is kind of explicit once we compute phi and a. And then we can finally deduce all the norm growth statements that we want on phi using degeneration of phi tilde. So for instance, if we want to prove that at infinity of phi grows, we can simply do further. This is bounded by phi t in at infinity times phi tilde in L1 in t. And we can explicitly compute that this decays in time. This is from that picture. So this must grow as the inverse of the. So in this sense, we can essentially get all the information that we want about the solution without actually getting hands on the solution. This is the wave packet testing method. It's kind of a generalization of Fourier analysis, if you think about it. So Fourier analysis is testing your solution to linear PDE against a simple phase. This is telling us how much of that frequency the linear solution has. And taking the time derivative is simply understanding how it changes in time. This is exact generalization. That the only difference is that now our equations are not translation invariant. So Fourier analysis simply does not apply, but the really nice substitute is given by this wave packet solutions. You can test your solution against wave packets to essentially get all the information that you want.
So you're actually constructing the nice decaying solutions to get the bad ones by duality.
Exactly. So these are really decaying in spaces lower than L2.
Mm-hmm.
Yes. They explicitly show all the properties that we want. Yeah. But it's essentially impossible to directly compute this quantity. Yeah.
Thank you.
Thank you very much.
Questions?
So in the beginning, you mentioned this well-posedness result of Pierre, Ben, and Jeremy.
Yes.
So how do you reconcile this with your result, right? Because you have a very general well-posedness result. So do they have some kind of lower term but with a higher power that is repulsively, or what's like the mechanism that these don't contradict each other?
Right, that's a good question. So they are actually not able to handle this so-called critical case. This they call as a critical case because the frequency is growing exponentially. This is not covered by their well-posedness. But what they did, and which is very nice, is they can consider so-called subcritical cases, and the degeneracy is of higher order. In this case, you can repeat this computation, and then you get that in this case, the frequency grows algebraically, which is much more tame. And then you essentially build your function spaces in a way that such algebraic growth can be accommodated. But they, it's kind of complicated.
In the critical space, I mean, case, there is no hope to get any kind of class where you might have.
So the solution, so if you look at their paper, even in the subcritical case, the function space is defined in the kind of renormalized coordinates. The coordinates in which this is being flattened out, and then you prescribe conditions in that coordinates. And in principle, you can imagine something like that. So let's say this is the degeneracy, point of degeneracy, and you want your solution to be very flat, and you need to kind of prescribe some kind of regions, in separate regions approaching the degeneracy. What is the frequency growth of the solution restricted to this sequence of regions, something like that.
So in principle, it's, I mean,
In principle, you can, yeah. But in the subcritical case, it can be done in a finite regularity space, kind of a heavily weighted finite overlap space that you can imagine. But in this case, it will be some kind of weighted analytic space.
so in principle,
In principle,
there might be actually some kind of blow up result, even, right? If you, or is it plausible? I mean, if you
yeah,
design your initial data very, very carefully, right? So that you have.
I think so. I think you can.
Right?
You can get, if you can get well-posedness,
Right.
well-posedness, blow up should.
Yeah,
Alright.
exactly.
Yeah, exactly. And then if you become super critical, then you can say that frequency actually blows up in time, which becomes shorter with initial frequency. So basically, there is no well-posedness unless the solution somehow has finite frequency, something like that. Of course, this is heuristic, but
But then you can also. So, Karen, you had a question?
Oh, yeah, well, I was just wondering, I mean, this is a very symmetric problem, so are you really looking at it in a half plane or, I mean, in a half line, or is that's just, I mean, in principle, phi is zero at the origin. I mean, you know what it's doing at the origin. Thinking,
So basically, I'm looking at the case where phi initially is supported away from the degeneracy. Yes.
yeah, I see that.
And the
Well, for example, if you look at it and it's supported away, say on the positive,
Mhm.
does it stay supported in the positive? Maybe that's a very simple.
sorry.
If the support of the initial condition is in the positive, does the support stay positive? Or I mean, I guess you're proving it's not
Yeah.
closed, so it doesn't have a solution, but I still.
Yeah, that's a good point. It is supposed to stay on the positive side.
Supposed to stay.
If you can get well-posedness, yes.
I see. Okay.
And we are only constructing approximate solutions, so we don't care, and our approximate solution, of course, stays in the positive.
Well, can you approximate it by something that is well posed? I mean, that was the first observation is, of course, it's really very different from on the left side and the right side. So there's no way of kind of getting rid of the singularity is somehow not just a singularity in a point. It really distinguishes behavior very different on the right and left somehow. I mean,
Yes, the behavior is actually very different.
yeah. So there's no way of getting an approximate solution that's well posed. Like, I mean, if it's a physical problem, lots of times you don't really need the solution of the problem. You just need some similar equation with the right properties. But this one doesn't really seem to have any approximations that are. Is that right? I mean,
I think if you had a very high viscosity, it will probably regularize the problem. No,
if you have very.
I
That's one thing.
images.
Or also you could do it in a half line, and then you could remove the singularity. I mean, you know, in other words, you can make X, you can add, if you do it at X greater than or equal to 0 and do a boundary condition, you could make it X cubed plus epsilon. And then that removes the singularity. But
Yeah, and I don't know what the boundary conditions
I see.
should be in that case, but it's a good point. But because some of these equations are claimed to be coming from physics,
Right.
and it's not completely clear if the models are still valid when the solution is allowed to be degenerate. For instance, in the case of shallow water equations, it corresponds to a situation where the height of water is 0, actually, at some point. Or in the magnetic problems, it corresponds to the situation where the magnetic field vanishes at some point. And then, of course, there's question of the very validity of these models. So,
Well,
I don't
presumably,
know.
you can figure out what the boundary conditions are by the reflection properties somehow. And so it does seem like you would get a well-posed problem in the half line if you did it carefully.
yeah, that could be the case.
Yeah.
Some situations.
Okay, there are no other questions?